Hey there, this is shoaib.saadat. You would have already seen some of my videos on my YouTube channel. This is one of the other videos that I've made basically, and the idea is to introduce you to something called as iVina. It's a project that I started a few days back, and the idea is basically to improve the experience, the docking experience that we have. For those of you who don't know about it, Autodock Vina is an outstanding, amazing software. It's an open source software which is being used basically for molecular docking. And the idea is to find out drugs or ligands who can be used in future treatment for a given condition. And it basically hastens the whole drug discovery process. If you already know about docking, I think then this becomes an easier tutorial for me to explain. If you don't, I think you can learn about it and then come back to this software and try to see if you can use it for your own use as well, or research projects. We've got a Facebook page as well, which you can visit here. It's basically facebook.com/iVina smart docking, and you can leave your comments and suggestions if you wanted to, and then I'll be more than happy to respond to those things. Alright, going back to the project. So how to get started? As you can see in the repository, we've got a few folders and a few files. All you got to do is go to this website and either click clone or download. If you're already familiar with GitHub commands, then you can clone the whole project. Otherwise, you can download a zip file, and once you've done that, you would end up in a folder like this. Now, the important file is this called as Autodock Python. I'm already assuming in this thing that you're already comfortable. You already have a Linux system, number one, and you're comfortable with some of the Linux commands. Trust me, they're not too hard to learn. You can learn them online by YouTube as well, but they're pretty simple to learn. The first few commands should include these, which would install yourself a good Python copy, or Python 3 recent copy with a Python pip as well. So once you've installed these, then the next step is basically to get yourself going and running. It's very simple. Go to your terminal and then type this command, which is basically going to create the important tools, or install the important tools which you need to get started with this software. Right, so here I am. This is my directory folder. It's the same folder that you already saw on GitHub repository page. And to get started, once I'm assuming you've already run these commands, sudo update, upgrade, and Python 3, the next thing basically has to be a setup command, which will create a complete setup for you. You can type this command, and you can use the tab for auto completion, and then it will basically ask you for your password. Once you've given your password, it will download the necessary or required repositories one by one and get your system ready for the whole process. Alright, so it's going to do all of that. I'm going to pause for a second and I'll be back. So the basic setup has been done. The second thing that we need to do basically is to do a typical directory structure. Now, interestingly, you've already done this part, so you don't need to repeat this project. But if you want it, you could actually type this command, and this will create a fresh copy of iVina for you in a separate directory folder. The next step is to be able to search the Campbell database. The Campbell database is an amazing repository which contains a huge number of drugs, essays, and papers basically that you can go through. But more importantly, it has got a huge collection of ligands, and you can find out the important ligands from there to be used in your project. So all you got to do is repeat the same commands, and Python 3 autodock python.py, and here you gotta write sc, which is search Campbell, and then press enter. It'll ask you what do you want to search for. So you can write, for example, antivirals in this case, and it will open a completely new tab for you. It will create a search query for you, and it will create the eligible list for medications that you wanted. Then you can further filter the medication list from here, or the ligand list. I'll create a separate video on how to basically use this database to the maximum effect as well, but let's proceed with the basic tutorial. Now, the next step basically is to prepare your protein receptor. Now, in my project directory, I've already created sample receptors and sample ligands. Now, as you can see, let's go through the project directory first, just to give you an idea of what's going on. Graphics folder is something which is basically just the graphics of this whole project, so it's nothing to do with the softwares or the ligand process, docking process. Ligand PDBQTs this is a folder which it's present at the moment, but usually you do not need to have this folder ahead of time. It's created automatically. The second folder is and this is basically the project folder which will be used for the docking process. Ligands SDF, this is the folder where you'll be saving all your SDF files. Now, SDF files is a structural definition file, and the idea is that each of this file consists of several ligands or drug molecule data. Like for example, in this case, this section contains the data for this drug molecule, which happens to be an antiviral called tenofovir. In the same way, it consists of this data of about hundreds of drug molecules that you can save in a single SDF file. How can you generate this SDF file? Is pretty simple. You can go to Campbell database, you can select a certain number of drug molecules that you want to be included in your docking process. You can go to download SDF on the right side here, and once you click here, give it a second, and it will create an SDF file, and then you can click from here, and then you can download your SDF files. So that's basically how you can create or generate your SDF files. Once you've done that, you can rename them, and you can just put them in this folder. Receptor is the other important folder, and here you are expected to provide at least a PDB file. Now you can find out all about PDBs by going to the PDB or Protein Data Bank repository. So here you can go to Protein Data Bank. You can find about any virus that you're interested in, or any protein molecule you're interested in, and then you can basically download this file in the form of a PDB format or Protein Data Bank format. Now, once you have done all of that, you can put your receptor here in this folder called receptor. So what's expected of you is that at least you should have a PDB receptor file in this folder. You should have at least an SDF file prepared in this folder. And that's pretty much it. That's all that's expected of you. Everything else will be taken care of by this app. Now let's go and continue with the tutorial process. So, okay, now let's prepare our protein receptor. Now, in order to prepare protein receptor, you got to use this command, which is again a simple command, which is basically -pp or -pp, which is prepare protein. And then you can give a certain receptor name, or you can simply type all to prepare all the receptors. Now, these receptors should be present in this folder called receptor. Now, in this case, as you can see, I've got just one receptor. It's called receptor underscore vp1.pdb, but you can have several receptors. Now, PDBQT is something which is generated by the system, so for all practical purposes, just imagine it doesn't exist. You just have to give a PDB file. All right, so let's go back and let's continue with the tutorial, and let's go to this command now. Let's create this command. Let's see if we can prepare our protein receptor or not. Now, since I already have this PDBQT file, I'll just delete it for the time being, so that you can see what's happening. All right, so the command is basically -pp, sorry, which is prepare protein. And in this case, I'm just typing all because I just want to be preparing all of these receptors. Let's go back to that folder so that you can see how it works. Now you press enter and just keep your eyes here as it will create these folders for you automatically. Now, the first thing it will ask you is that which process are you going to use? Are you going to use Babel, which is an outstanding resource tool which can be used to convert different molecular formats one to the other? It's basically asking you, are you going to use Autodock tools? And interestingly, if you were to do it yourself, you would actually have to open Autodock tools, and it will actually take you a lot of time. So just to give you an idea of how much time it can take, I'm just going to just stop it for a moment just to give you an idea. This is the Autodock tool software. If you were to do it yourself, you'd have to drag this PDB here, and then you'll have to prepare it like any other molecule. You'll have to you'll have to delete the water molecules, you'll have to basically add hydrogen molecules, and then depending on what do you want, you can add polar only. You'll have to calculate the gastric charges as well on this molecule, and you'll have to make sure that these charges are equally distributed by going to this and then spreading the charge deficit on all the residues equally. And then once you've done that, you'll have to go to the grid box. In fact, this is the later step, not that, but you'll have to go to the grid box and then choose the macromolecule, and then you'll have to save it as a PDBQT. And it will automatically find out any non-bonded atoms as well, and it will ask you to save it as a PDBQT, and then there you go. Now that is not too many steps, but imagine if you have to do it for like hundreds of receptors. I'm just going to close it now, and I'm going to show you that it does it automatically, the tool that I've created, without you actually needing to do any of that. So we are here again. In these options, you can use either 1 or 2. 1 is a pretty fast option. It will immediately create and do most of these steps for you, but 2 is a bit more accurate, and I'll go with the Autodock tools method here. Now it's asking you how many chains do you want. It already identifies that your molecule has got just one chain, and it's called 3. I mean, in this case, in my molecule. So again, you've got two options. You can just simply type all to include every chain in your protein molecule, or you can basically pick the chain from here, and you can write it separated by space. For example, chain A, chain B, and all that. In this case, I'll just type all. Keep your eye here on the folder structure, and you'll see several of these things happen. And here you can see it has automatically done all of those steps that I did by opening Autodock tools, and it has created some amazing files for you already. Now let's go here. What it did was you had an original PDB. It has created a raw PDB folder and put that original into that folder, and then it has created the new transformed PDB and its equivalent PDBQT. We will be using this PDBQT eventually in our docking process. So it has done that already. You don't need to do anything. We've already prepared our protein. The next step is to create PDBQTs. Now PDBQT is a simple PDBQT, but it's got charges in it as well. And again, the steps are pretty simple. Before you do that, make sure in your ligands SDF folders, you should have an SDF file. And you don't need this PDBQT folder. So in fact, just to show you that you don't need it, I'm going to delete this PDBQTs folder. And then we will be creating this folder from anew. Now let's go back and do this step. And in this case, you just need a single P to be able to carry out this step. So let's go back here. Now keep an eye here, and you will see a PDBQT folder being created. All right. So I've already typed the command /p, and I'm going to type all because I want to do this process on all the SDF files that I've got in the ligands SDF folder. All right, now it's again going to ask you how you're going to do it. In this case, again, there are two options. You can use Autodock tools. You can use Babel. I would recommend using Babel because it's fast, number one, incredibly fast, and number two, it's relatively a bit more accurate, interestingly. So all right, I've chosen one here, and now keep an eye on the folder structure. It will create that for you. It is done, and there you go. So it's created a folder called PDBQTs, and if you go in, it's created all the PDBQTs that you require. Now you might ask, why do you need these PDBQTs? You actually require all of these PDBQTs, either receptor or ligands, to be able to carry out the final docking, because that's how Autodock basically does the docking. It requires these charged files. Right, so we've done these steps. We've prepared our receptors, we've prepared our ligands. The next interesting bit is basically to be able to create a search box. Now, what is a search box? Now, under normal circumstances, what you would do is that you would actually open the Autodock tools. I'll show you how can you create a search box as well. But again, I'll show you my tool actually creates it automatically for you. So probably you don't even need to do all of these steps. So like in this case, let's go to the receptor and let's take this PDB file. Now, in order to create a search box, you need to first select your macromolecule, which in this case, this is our macromolecule. And I'll just select yes, just to hasten the whole process. And now you need to go to grid and you need to create a grid box. If you can see here, there is this small box. Let me increase the size of it so that you could actually identify. There it is. So this is the box basically. And the idea is that wherever you place this box will be the place where you'll be searching for any given specific receptor docking site. Now imagine you've got a receptor site here, which is really important on one side. Then in order to carry out docking, or in order to check basically whether any of the ligands that you've selected dock successfully onto this side, you'll have to make sure that your box actually covers that area completely, like this, for example, in this side, and then you'll try all of your ligands in this area. The important parameters is the position of the box and importantly the size of the box. The more the size, the more the search area, and it will take a lot of time. So in either way, you'll have to first identify it. The next step is once you've identified the box, you need to make sure you save its grid dimensions, and you can do it by going to File and then Output Grid Dimensions File, and then you can basically save it by giving any name. Now you can use this process, which is fine, and in fact in some of the cases you'd want to do that. In that case, I would encourage you to do the same process exactly as we've done until now. Output the dimensions file, go to the project folder, the Vina project folder, and then save your file with this prefix. So make sure that you've got grid underscore and then you give the exact name of your receptor as you have saved it. For example, in this case, we have got receptor underscore VP1, capital VP. So you just need to write in the same way receptor underscore capital VP1.txt and then save it in the root folder, in the main Vina project folder. And that's all that you need to do. But say, for example, you've done the literature review and you find that the important site where we should be actually trying to dock is somewhere around, say in this case, we've got 30. So say glycine 30. So in this case, if I've selected, as you can see here down on the bottom, this is the area where glycine is selected. Let's select another residue here, just to increase the dimensions. So say, for example, we've got glutamic acid here, which is around here. So we've got two of these selected. As you can see, these yellow selections. One of them is glutamic and the other one is this other one, which is the glycine. Now the box basically should actually cover both of these areas. It should be big enough. The tool basically helps you to do that. You don't need to do or create a box all by yourself. All you need to know is the residue numbers. In this case, as we just saw, it's 30 and 60. Now let's go back to the tutorial. Now, in order to basically make this grid file, this is the code that you need to do. And just to give you an idea, let's go back to this Vina project folder. In this Vina project folder, I already have a file called grid receptor, but I'm going to delete it again just to show you how the tool creates it automatically. So let's open the terminal here. I'm going to clear the terminal. All right, now let's create that command. It's Python Autodock Python -g to create grid file, and in this case I'm just going to type all because I want to create it for every receptor. It'll identify the PDB and then it will create a receptor for it automatically. So let's go for it. I'm going to click yes. Now it's going to ask you about the box dimensions. Default is about 5 angstroms wide and all the dimensions. I'm just going to continue with default, or you could type your own dimensions. The more you type, the bigger the box is going to be. Now it's basically going to ask me about the residues that I just saw. So as we already saw, there were two residues, 30 and 60. I'm going to just separate them by a space, and this is how you should be doing it as well, and press enter. Now before pressing enter, just keep an eye on the folder structure. It will automatically create that grid file for you. All right, so it's basically created that grid file. It's given you given you details here as well, but it's created this grid file here, which is this file, and it automatically uses this grid file in the next step as well. The next step is basically the real process, which is creating the Autodock process. Before that, I'm just going to go back to the ligands PDBQTs, but just to improve the speed of the process, I'm just going to leave a few here and delete the rest. All right then, so let's go to the next step. The next step is Autodock 80. So that's the command. So let's write that command. And in this case, I'm going to again select all. Otherwise, you can select a certain receptor where you want to carry out the Autodock process on. I'm going to do all, and let's give it some time. First, it asks basically about the exhaustiveness. Again, it's up to you. The standard could be 8 or 10. The more exhaustive you keep, the more exhaustive search it does and creates multiple conformers. I'm just going to hasten the process and just choose 2, but you can actually leave it to default. Now it's doing the whole process. It's identifying the whole thing, automatically finding out the box grid dimensions, and it's basically creating these conformers one by one for the 2 receptors. Meanwhile, let me just show you the directory structure. It has automatically created a folder called outs_receptor vp1. This is the folder where you'll be finding most of your final log files. If I open it up, it's already created one of the logs. It's the log for one of the ligands that we already tested. Now it's created the second log as well. Now this is carrying out this process for the second ligand as well. So one by one it does it for both the ligands and creates the out files. There you go. We're done because we just had 2 ligands, and we chose a very low exhaustiveness level as well. So this is a single log entry, but we want to find out about the complete results. Now, if under normal circumstances, you'll have to go through every log one by one, find out the lowest value in that, and then open the second one as well. And this is basically in kilocalories per mole. It tells you about the binding affinity. The lowest, the better. So in this case, I'll basically have to open every log file and find out the lowest value, and then choose that as the receptor of choice. The ligand of choice. Now, you don't need to do this again with the tool. All you got to do is follow the next step, which is creating the results file. So let's go back. Go back to terminal, and here just choose -r all, again creating for every receptor. There you go. It's already created a file here in the folder structure. It's called results_the receptor name.txt. So you can open that, and it gives you this file, and it has already selected for you basically the best ligand. It's basically saying the lowest kilocalorie per mole energy levels, or highest binding affinity, came out for this ligand, which is 26. But for any given reason, if you didn't know what was this ligand and what is the name of this ligand, what drug, what formula, what is log P, that kind of detail, then you can follow the next step, which is basically creating a drug table, a lookup drug table basically. And the command is dt. Let's create that as well, and I'll show you a complete final result in that case. Here, instead of R, I'll just do dt and all. Now keep an eye on the folder structure, because there will be new files created. There you go. Now it has created some drug table files. Each drug table file basically consists of a complete list of your medications or ligands, and it gives extra details about them. Ideally, you can use either of them, but I would recommend using to basically get started with this one, drug table by dollars. And the idea is that it covers almost every kind of ligand and doesn't miss any of that as well. And it gives you the exact names that those ligands had in the STF file. Now, how to read the whole thing? You open your results on one side, and you open your drug table by ligands on the other side. Now here you can see the best ligand was 26. You can find out, and it had basically a pretty good binding affinity, minus 9.3 in this case, for example. Then I would find out this chosen covert 26, and I can find out by following this column, which is this one. So here I've already found which ligand I'm talking about, and then we can use this to further explore. Or alternatively, we can open the standard drug table, and still I can go ahead and find out that specific drug, and it happens to be this drug, delaviridine. Or I could actually use by name as well, and then I could go into the same place and I can find that this drug basically happens to be delaviridine. In either case, these drug tables basically help you to find out which drug that was, what is the binding affinity, and then at the end of the day you can further refine your results. Now your outs folder has the most important things. It has the chosen conformers. If I were to open PyMol in this case, so let's open PyMol and let's show you the chosen binding conformers. What you can do is simply drag this PDBQT in the outs and just put it here. It will automatically place the ligand where it's supposed to be. Now let's go back and open the receptor. Now in this case, you can open any of these files. I'm just going to open the PDBQT just in case, and just drag it here. Now here you go. As you can see that it did the docking process, and it has finally docked this drug in a certain specific manner to this specific protein. And if you remember, we chose our box down there with some of the residues on the bottom, and it automatically docked on those sites as we intended. Right, so, and not just that, you can also run a small movie where you can find out all the different docking positions that it tried. Well, it has tried some weird positions as well, apparently, but the reason being our box was a bit wider, that's why. Most of the docking has been around the same place as we expected, and the best conformer is basically the first one. And then you can also identify about the bonds that it's making. There are other software packages that could be used as well, but in this way you can carry out your docking automatically. And be able to find out the results that you want in a quicker and faster way. I'm thinking about improving it further as well. So if you have got any ideas or you want to contribute to the project, you're most welcome. You can come to this link and then you can submit your pull request, and then we can move on from there. Thank you so much. Please leave your feedback. I would be most receptive, and I'd be extremely happy and thankful if you've got any suggestions for me to improve this project even further. Thank you so much for watching this video. I hope you have an amazing time. Take care of yourself, and please do not forget to cite this GitHub repository if you use it. Until next time, goodbye.